The cosmos has a way of sending us postcards, not just in the form of ancient light from distant stars, which takes millions of years to cross the gulf, but something far more tangible, something you could, in theory, reach out and touch. We are accustomed to thinking of our solar system as a self-contained island, an isolated bubble of planets, moons, and asteroids orbiting a single, familiar star. The distances to even the nearest neighboring stars are so immense they defy easy comprehension, measured in light years of cold, empty vacuum. For all of human history, everything we studied in our skies belonged to this local family, born from the same primordial cloud of gas and dust as our own Earth. But the galaxy is not static. It is a dynamic, churning system of over 200 billion stars, each with its own potential retinue of planets, comets, and asteroids. And sometimes, through gravitational nudges and ancient cosmic billiards, a piece of one of those distant solar systems is ejected, cast out to wander the dark expanse between the stars. Sometimes, those postcards are delivered by messengers traveling for billions of years across that vast, dark expanse. These are time capsules, carrying pristine material from their home system, unchanged by the warmth of a nearby star for eons. Today, we are living through the arrival of just such a messenger. This isn't a theoretical concept or a computer simulation. It is a real, physical object, currently hurtling through our cosmic neighborhood. Its arrival is a profound moment, a brief intersection of our own journey around the sun with the epic galaxy-spanning voyage of a lonely traveler. Its name is 3I/Atlas. This is not just another rock or snowball in our cosmic backyard. The comets we are familiar with, like Halley's or Hale-Bopp, are members of our own solar family. They reside in the distant icy realms of the Kuiper Belt or the even more remote Oort cloud, a vast spherical shell of icy bodies that technically marks the gravitational boundary of our sun's influence. While their orbits are huge, they are still closed loops, forever bound to our star. They are natives. 3I/Atlas is different. It is an immigrant. It is the third object ever confirmed to have journeyed here from another star. Its trajectory is not a closed ellipse, but an open-ended hyperbola. It is moving so fast that our sun's gravity can bend its path, but can never capture it. It will swing past the sun, cross the paths of our planets, and then continue on its journey, exiting our solar system to disappear back into the interstellar void, likely never to return. That makes it an interstellar visitor, a rare and precious gift from the galaxy. Its rarity cannot be overstated. For centuries, we have scanned the skies, but only in the last decade have our survey telescopes become powerful and systematic enough to spot these faint, fast-moving intruders. Finding one is a testament to both the vastness of space and the power of our technology. Its arrival gives us a front-row seat to study a piece of a planetary system that is not our own. Imagine being an archaeologist and suddenly being handed a perfectly preserved artifact from a completely unknown civilization. That is the scale of the opportunity before us. This object was formed in a protoplanetary disk around a completely different star, under conditions we can only guess at. We get to analyze its composition, trace its path, and unlock the secrets it has carried on its long, cold journey. By pointing our most powerful telescopes, like the James Webb Space Telescope, at this visitor, we can perform a kind of cosmic chemistry. We can see what ices it's made of, how much water, carbon dioxide, or carbon monoxide it contains. Is the recipe for comets universal, or does each star system cook its icy bodies with a unique chemical signature? These are questions we could only dream of answering until now. Until recently, everything we knew about comets came from our own solar family. We had a sample size of one, our own system. It was impossible to know if our comets were typical or strange. We had no basis for comparison. It was like trying to understand all of humanity by studying only your immediate relatives. You'd get a picture, but it would be incomplete, biased, and missing the vast diversity of the wider world. But 3I/Atlas, alongside Oumuamua and 2I/Borisov, is writing a new chapter. The first visitor, Oumuamua, detected in 2017, was a complete enigma. It was small, oddly shaped, and showed no visible signs of outgassing like a typical comet, leading to intense debate about its nature. Was it an asteroid, a nitrogen iceberg, something else entirely? Then, in 2019, came 2I Borisov. It looked and acted much more like a conventional comet, complete with a fuzzy coma and tail, giving us our first real chemical analysis of an object from another star. It was reassuringly familiar, yet subtly different from our own comets. Now, we have our third data point. The name itself tells the story. The I stands for Interstellar, a formal designation for objects on a hyperbolic escape trajectory. The 3 marks the third one found, an atlas. That's the name of the survey that discovered it. The Asteroid Terrestrial Impact Last Alert System. It's a network of robotic telescopes in Hawaii, Chile, and South Africa, designed to scan the entire sky every night, searching for asteroids that might pose a threat to Earth. In doing its job, it stumbled upon this ghost from another star. Each time one of these visitors arrives, it is an incredible opportunity to answer big questions about the universe. How common is planet formation? Are the building blocks of life, like water and organic molecules, which we know comets carry, distributed widely across the galaxy? By studying these messengers, we are, in a very real sense, studying the conditions for life elsewhere. 3I Atlas is more than a comet. It is a clue, a piece of a grand cosmic puzzle, and a humbling reminder that our solar system is just one small neighborhood in a vast, interconnected galactic city. And for a brief moment, we have a visitor from another part of town. Every major discovery begins with a single moment of observation. For 3I/Atlas, that moment came on July 1st, 2025. Credit goes to the Atlas Survey Telescope in Chile and its counterpart in Hawaii. Their job: scan the night for moving objects, asteroids and comets for planetary defense. Atlas flagged a faint object moving unusually. Multiple images over hours and days revealed its path. Not a closed loop, but a hyperbola, the smoking gun of an interstellar origin. It would sweep past the sun and head back into the void, never to return. Confirmation transformed it into 3I/Atlas, our third interstellar object. Observatories worldwide pivoted fast to capture every possible photon. Every visitor to our solar system carries a story, a cosmic postcard from a distant unknown star. For the interstellar comet 3I Atlas, that story is etched into the very fabric of its journey across the galaxy. To read it, we must become celestial detectives, asking the most fundamental question: where did you come from? The answer, it turns out, is written in the language of gravity and motion, a tale told by its trajectory through space. Unlike objects born in our own solar system, which follow predictable, closed ellipses around the sun, 3I Atlas arrived on a hyperbolic path, a clear sign that it was just passing through, a temporary guest on a voyage that began long ago and far away. This path is our primary clue, a breadcrumb trail leading back through time and space. By meticulously measuring its position and velocity, astronomers can rewind its motion, tracing its path backward in time. As we follow this trajectory out of our solar system and into the interstellar void, a clear direction emerges. The comet's path points us back toward the constellation Sagittarius, a region of the sky famously home to the heart of our Milky Way galaxy. This immediately sparks a tantalizing thought. Did it come from the supermassive black hole, Sagittarius A? The answer is a definitive no. While its origin lies in that general direction on our sky, it did not emerge from the chaotic environment of the galactic core itself. Instead, its journey began somewhere in the vast, star-filled expanse that lies between us and the galaxy's center. The direction is a signpost, but the real story of its origin is woven into the subtle details of its flight. To pinpoint its home, we have to consider the structure of the Milky Way itself. Our galaxy isn't a uniform sphere of stars. It's a complex, layered system. The most prominent feature is the galactic disk, which is itself divided into two main populations. There is the thin disk, a dense, flat plane where we reside. It's a bustling stellar nursery, rich in gas and dust. where new stars, many like our Sun, are actively being born. Then there is the thick disk, a more diffuse, puffy halo of stars that surrounds the thin disk. These are ancient stars, relics from the galaxy's youth. By analyzing the angle and speed at which 3I Atlas approached us, astronomers can deduce which of these populations it most likely came from. Its path, inclined relative to the main plane of the solar system and the galaxy, suggests it could have originated in either the thin disk of young stars or the thicker, older disk. Each possibility tells a radically different story about the comet's age and history. If it came from the thin disk, it might have been born in a star system much like our own, and relatively recently in cosmic terms. But if its origins lie in the thick disk, the implications are staggering. The stars of the thick disk are ancient, typically between 7 and 10 billion years old. If 3I Atlas was born around one of these stars, it would mean this icy wanderer is profoundly old, potentially billions of years older than our entire solar system, which formed a mere 4.6 billion years ago. It would be a primordial relic, a pristine sample from a time when the chemistry of the galaxy was fundamentally different. This single object could hold clues about the building blocks of planets from a much earlier cosmic era. But how does an object like this become a galactic nomad in the first place? The process is one of controlled chaos. In the early turbulent days of a planetary system, countless icy bodies, or planetesimals, swirl around their host star. The gravitational landscape is a complex dance floor, dominated by the pull of large, newly formed planets. A small comet, venturing too close to a gas giant like Jupiter, can find itself caught in a gravitational tug-of-war. It doesn't collide. Instead, it engages in a gravitational slingshot. The planet's immense gravity and orbital momentum act like a catapult, accelerating the small body to incredible speeds, fast enough to overcome the star's gravitational pull and achieve escape velocity. Kicked out of its home, it begins a lonely, multi-billion-year journey through the dark spaces between the stars. For eons, perhaps for billions of years, 3I Atlas drifted through the interstellar medium. This was not a quiet journey. It was constantly bombarded by high-energy cosmic rays. Protons and atomic nuclei accelerated to near the speed of light by distant supernovae. This relentless shower of radiation didn't destroy the comet. It transformed it. The cosmic rays penetrated its surface, breaking down simple molecules like water, carbon monoxide, and methane ice. This process, known as irradiation, triggered a cascade of chemical reactions, forging more complex organic molecules on its surface and just beneath. The comet's outer layers were chemically processed, developing a crust that preserved the more pristine, volatile ices deep within its core. This long journey didn't just change its location, it changed its very chemistry. The journey of 3I Atlas reminds us that our galaxy is not a static collection of isolated islands. It is a dynamic, interconnected ecosystem. Objects like this roam the Milky Way by the trillions, acting as cosmic messengers, exchanging the fundamental building blocks of planets between star systems. The very materials that formed Earth may have been delivered by comets, and here we see that this process isn't confined to a single solar system. It's a galaxy-wide delivery service. Material is constantly on the move, ejected from one system and, after millions or billions of years, potentially captured by another. This single fleeting visitor is a physical testament to the grand, galactic cycle of matter, a story of ancient origins and endless wandering. When a rare guest arrives, you bring out your best instruments. The James Webb Space Telescope, massive golden mirror, eyes in infrared, perfectly suited to capture faint heat and chemistry from 3I/Atlas. Breaking its light into a spectrum revealed a chemical fingerprint. Headline: a CO2-dominated coma with a CO2 to H2O ratio of about 7.6 to 1, among the highest seen. JWST also saw water, carbon monoxide, carbonyl sulfide, signatures of water ice, and fine dust. Outgassing was stronger on the sunward side as the comet heated. High CO2 may hint at long radiation exposure in interstellar space, selectively stripping fragile ices. Each new object is a crucial data point, mapping comet diversity across the galaxy. The study of 3I/Atlas was no one telescope show. NASA orchestrated a campaign using assets already en route across the solar system. On September 8th and 9th, Psyche captured 4 observations over 8 hours from about 33 million miles away. Those frames helped refine the comet's trajectory. Lucy contributed vantage points impossible from Earth. Different spacecraft locations enabled precise parallax to pin down position and speed. As it passed behind the Sun, Stereo watched Sept 11th to Oct 2nd, SOHO from Oct 15th to 26th. They tracked activity and brightness through solar glare, ensuring a continuous record. A coordinated, multi-mission effort seized a rare scientific opportunity. The collaboration extended to Mars. ESA's ExoMars TGO, orbiting since 2016, was perfectly placed to observe. Between October 1st and 7th, controllers repurposed its camera to image deep space. They captured the faint interstellar comet, no small feat for an instrument not designed for it. The long baseline yielded powerful parallax, improving predicted location precision by a factor of 10. For the first time, astrometry from a spacecraft orbiting another planet was accepted by the Minor Planet Center. It proved orbiters can double as a deep space observatory network. That accuracy maximized precious observing time once the comet emerged from the sun's glare. For skywatchers, 3I/Atlas became a game of celestial hide-and-seek. After July's discovery, it slid into the sun's glare through September and October. We relied on Stereo and SOHO while Earth observers waited. By mid to late November, it returned, first low in the morning sky before sunrise. Around November 11th, it was spotted again, rising a bit higher each day. The International Asteroid Warning Network launched a special astrometry campaign from November 27th through January 27th. Closest approach arrives December 19th, at about 1.8 astronomical units, roughly 170 million miles. Through December, it moves from Virgo to Leo, likely dimmer than magnitude 12. You will need a decent amateur telescope, dark skies, and a good star chart to glimpse its ghostly glow. Strange visitors spark debate. That is how science strengthens itself. Harvard's Avi Loeb highlighted puzzling aspects: brightness, a precise-looking path, and early ambiguity and outgassing. Such questions force rigorous cross-checks of data and methods. But JWST's detections, CO2-dominated coma plus H2O, CO, OCS, ice, and dust, strongly support a natural comet. Its brightening near the sun and enhanced sunward outgassing are classic cometary behavior. Consensus from NASA, ESA, and most astronomers. An extraordinary comet, but a comet nonetheless. Its significance is not artificiality. It is that this authentically alien object preserves the chemistry of another star's nursery. The universe has sent us a message in a bottle. With the passage of 3I/Atlas, we are finally learning how to read it. This visitor from another star system, like Oumuamua and Borisov before it, is more than just a celestial curiosity. It is a physical sample, a direct probe of a planetary system hundreds or thousands of light years away. For generations, our understanding of how planets form was based on a single example, our own solar system. We had theories, models, and simulations, but they were all calibrated against one data point. Now, that's changing. Each interstellar object that passes through our cosmic neighborhood carries with it the chemical fingerprint of its birthplace. It is a relic, a leftover building block from a time when planets were just beginning to coalesce around a young star. By studying its composition, we are essentially performing remote geology on an extrasolar world. These objects help us answer fundamental questions. Are the processes that built Earth, Mars, and Jupiter common throughout the galaxy? Or are there wildly different pathways to building a solar system? The high abundance of carbon dioxide in 3I/Atlas, for instance, suggests it formed in a region of its home system that was very different from where our own comets formed. This diversity is the key. It forces us to refine our models of planet formation, accounting for a wider range of initial conditions and chemical inventories. We can now compare the compositions, sizes, and trajectories of these interstellar visitors to build a statistical sample. With just 3 objects, we've moved from anomaly to a dataset. With 10 or 100, we could begin to map the chemical geography of our corner of the Milky Way, understanding how planetary systems form and how often they eject debris into the vastness of interstellar space. This journey of discovery inevitably leads to one of humanity's most profound questions. Are we alone? The concept of panspermia, the idea that life itself, or at least its essential building blocks, can travel between star systems, has long been a subject of speculation. Interstellar comets like 3I Atlas provide a plausible delivery mechanism. We know they are rich in water ice and carbon-based molecules, the very ingredients for life as we know it. While there is absolutely no evidence to suggest 3I Atlas carries life, its journey demonstrates that the galaxy is a connected place. The raw materials for biology are not confined to a single planet or solar system. They are being constantly exchanged, hurled across the interstellar medium by gravitational encounters. Could a comet like this have seeded a young Earth with the compounds that kick-started life? It's a possibility that scientists take seriously. The same physics that shaped our world sculpted this visitor from afar. Its journey confirms that the fundamental chemistry needed for life is likely widespread. It doesn't mean life itself is everywhere, but it strongly suggests that the potential for life is. Each new interstellar object we study allows us to test this hypothesis, to analyze its organic inventory, and to understand if these cosmic messengers could truly be the seeds of biology, scattered on the galactic winds. So, what comes next? The era of interstellar object science is just beginning. The discoveries of Oumuamua, Borisov, and Atlas were, in many ways, fortunate accidents made by surveys designed for other purposes. But the next generation of observatories will be true interstellar hunters. The Vera C. Rubin Observatory in Chile is poised to revolutionize this field. When it begins its legacy survey of space and time, it will scan the entire visible southern sky every few nights with unprecedented depth and speed. Its powerful camera will create the deepest, widest movie of the universe ever made. Scientists predict that the Rubin Observatory will find dozens, perhaps even hundreds, of interstellar objects every year. Instead of being surprised by their arrival, we will have a steady stream of visitors to study. We will be able to detect them much farther out, giving us more lead time to coordinate observations with powerful telescopes like the James Webb Space Telescope. This will turn a trickle of data into a fire hose, allowing us to build a comprehensive catalog of our interstellar neighbors and truly understand their origins and diversity. But why stop at just looking? The ultimate goal is to visit one of these objects up close. Missions are already being designed for this very purpose. Concepts like the European Space Agency's Comet Interceptor are designed to wait patiently in space, parked at a stable gravitational point. When a suitable interstellar object is discovered with enough warning, the spacecraft will be deployed on a high-speed trajectory to fly by it, capturing the first-ever close-up images and direct measurements of a messenger from another star. Such a mission would be a monumental achievement, transforming our understanding of these enigmatic travelers. It would be our turn to send a probe out to meet the message in a bottle, to analyze its contents directly, and to read the story of another world written in ice and dust. For now, 3I Atlas continues its silent journey back into the interstellar void, its brief encounter with our sun now a fading memory. It poses no danger. At its closest, it remained about 170 million miles away, nearly twice the distance from the Earth to the Sun. Our curiosity was entirely guilt-free, but its visit was a profound gift. It is an invitation to marvel, a call to look up, be curious, and take part in the grand process of discovery by reading, by observing, by wondering. The same universal laws connect our world to the distant star system that this comet once called home. Its passage reminds us that we are part of a vast, interconnected cosmos, one that is slowly, visitor by visitor, revealing its secrets to us.